Hey everyone, and welcome. So in engineering, you run into some classic problems all the time, like how do you move a fluid over a huge distance or pump it way up high? Well, you need a ton of pressure. But what happens when the one pump you've got just isn't cutting it? Today, we're going to dive deep into the textbook engineering solution for that exact situation.
So here's how we're going to break it down. First, we'll lay out the pressure problem itself. Then, we'll look at the elegant series solution. After that, and this is the fun part, we'll visualize how it all works with performance curves. Then, we'll get serious and talk about real-world risks before we wrap it all up with the key things you need to remember. Let's jump in.
All right, first up, the pressure problem. This is the whole reason we're here, the fundamental challenge we need to solve.
So picture this. It's a classic scenario, really. Your system, whatever it is, needs more pressure, or what engineers call head, than any single pump you have can possibly deliver. What do? It's a core question, and thankfully, there's a really effective answer.
And that answer brings us right here, to the series solution. You know, the principle behind it is beautifully simple. You just connect the pumps one after another, and their pressures literally add up.
So what does a series connection actually look like? It's exactly what you see here. The outlet, or the discharge, from pump number 1 feeds right into the inlet, the suction, of pump number 2. What this means is that the second pump isn't starting from zero. It's getting fluid that's already pressurized and then boosting it even higher. It's a team effort.
Now, to make sure we're all on the same page, let's do a quick comparison. The series connection we're talking about today, it's all about jacking up the pressure, the head, while the flow rate pretty much stays the same. A parallel connection is the total opposite. That's what you use when you need more flow rate at roughly the same pressure. If you remember one thing, remember this. Series adds head. Parallel adds flow. Simple as that.
Okay, now for the heart of it all. We're going to see how this works visually by looking at pump performance curves. This is where the theory really clicks and comes to life.
But wait, before we jump into the graphs, let's lock down one key term, head. In the pump world, head is just a super practical way of talking about pressure. The easiest way to think about it is this. It's the maximum height a pump could push a column of water straight up into the air. So more height, more head means more pressure. Got it? Good.
All right, check out this graph. This is our baseline. That solid black curve showing you the performance of just one pump, how much head it creates at different flow rates. Now that dashed line is the system curve, and it basically represents how much pressure you need just to fight against all the friction in your pipes. And right where they cross, that's the pump's operating point. It's the actual pressure and flow you're going to get in the real world.
So how in the world do we graph what two pumps do together in series? It's actually just simple addition, but vertical. First, you just pick any flow rate you want on the bottom axis. Then you go up and see what the head is for a single pump at that flow. And since we've got two identical pumps, you just double that head value and make a new dot. You do that a few times, connect the dots, and you've got your new curve.
And voila, here's the result. That new green line is our combined series pump curve. See how it's basically the original curve just lifted straight up? This is the visual proof of that core idea. For any flow rate you pick, two pumps in series are going to give you about double the head.
So what does this actually mean for our system? Well, look at the new operating point, where our new green curve crosses the system curve. We get a massive increase in head. That's our pressure. But look, only a tiny little bump in the flow rate. Now, why is that? It's because of that system curve. As the flow gets faster, the friction in the pipes shoots up. So even with all that extra pressure, we're only able to shove a little bit more water through the whole system.
Okay, we've got the theory down, that's great. But now it's time to get back to the real world. Because in practice, there are some incredibly important safety checks that you absolutely cannot ignore. When you're setting up pumps in series, there are two critical safety checks that are non-negotiable. Getting either one of these wrong can lead to some seriously catastrophic failures.
You know, the source material for this explainer had a fantastic quote that just perfectly sums up the first major risk. It says, "Many systems fail because the pump is strong but the pipe isn't." That is such a common and very costly mistake.
So risk number 1 is all about the pressure rating. The final pressure coming out of that second pump is the combined force of both pumps working together. This is crucial. You have to verify that every single component downstream, we're talking the pipes, the flanges, the pump casings themselves, everything is rated to handle that much higher pressure.
Now, the second big risk is something called cavitation. This is basically when the pressure at the pump inlet gets so low that the fluid actually starts to boil,
forming these tiny, destructive vapor bubbles. When those bubbles collapse, they do it with incredible force, and they will literally eat away at the pump from the inside out. Now, in a series setup, if pump number 1 starts to cavitate, it's just going to feed that stream of destructive bubbles right into pump number 2. You get a chain reaction of damage that can wreck both machines.
All right, let's bring it all home. We're going to move to our final section and boil everything down into a clear, simple blueprint for success.
This slide really wraps it all up in a neat little package. The concept? Use a series connection when you need more head. The calculation? Just add the head values vertically on the pump curve. The operation? Your system's operating point is going to move way up, giving you more pressure. And the most important part, safety. First, double-check that everything downstream can handle the combined pressure. And second, make sure pump number 1 has enough NPSH, or net positive suction head, to prevent that nasty cavitation we just talked about.
And that just about does it for us. We've figured out how to solve for more pressure. But that might get you thinking, what if your problem isn't pressure? What if your system is starved for more flow instead? Well, that's a whole other fascinating story for another time.